Good morning from India. My name is Mehwish Hassan, and I, being the co-chair of the session, I welcome you all to this webinar, GeoLive 2021. On behalf of School of Civil Engineering, Lovely Professional University, Indian Geotechnical Society, IGS Jalandhar Chapter, and Department of Civil Engineering, Dr. B.R. Ambedkar, National Institute of Technology, Jalandhar. I welcome you for your session on the topic Construction in Geotechnical Engineering using Geosynthetics and Alternative Materials. This session is chaired by Dr. Amit Srivastav, Professor and Head of School of Civil Engineering LPU, and will be co-chaired by me. Now, I request Dr. Amit Srivastav to take over the session and start the proceedings. Thank you.
Thank you, Mahvish, for your nice introduction and start of the session. It gives me an immense pleasure to introduce Professor Palmeira to our audiences who have joined us on this Google Meet platform. Professor Palmeira obtained his BSc and MSc degree in civil engineering from Federal University of Rio de Janeiro, Brazil in 1977 and 1981. He holds a PhD degree in civil engineering from University of Oxford, UK in 1987. In both his MSc and PhD thesis, research on the use of geosynthetics for soil reinforcement. He was a member of the Council of International Geosynthetics Society for 12 years and chair of the Education and South American Activities Committees of that society. He also founded the Brazilian Chapter of IGS, International Geosynthetics Society, and was its first president. Professor Palmeira has in journals and conferences on different applications of geosynthetics in geotechnical and geoenvironmental engineering. He is a member of Brazilian Academy of Science since 1987 and has received the Scientific Merit Award from the Brazilian Presidency in 2008 and was 2 times recipient of IGS Award. He is a member of the editorial boards of the journals Geosynthetics International and Geotextiles and Geomembranes, editor of journals Soils and Rocks, published by the Brazilian Geotechnical Society. And he has served as time he is professor of civil engineering at the University of Brasilia, Brazil. Thank you very much, sir, joining us on this platform and agreeing to share your expertise in the field of geosynthetics and alternative materials. I request you to please take over the session and deliver your talk on the topic Construction in Geotechnical Engineering using Geosynthetics and Alternative Materials. To the audience, if you have question, you can put the same in the chat box or you may ask at the end by unmuting yourself. Your questions will be taken by the expert at the end. Till then, I request you all to keep yourself muted and your video should also be turned off. Once again, thank you, sir.
Thank you. I hope you all can see my presentation. I would like first to thank the organizing committee of the GeoLive 2021 for the invitation. It's a great pleasure for me to present this work to you all. The title of the presentation is Construction in Geotechnical Engineering using Geosynthetics and Alternative Materials. Let's see the contents of the presentation. The content will start with a brief introduction and some examples of sustainability of works with geosynthetics, geosynthetic reinforcement of marginal soils, and alternative construction materials, some examples in unpaved road constructed with marginal soil and recycled construction demolition residues as fill materials, An example of paved roads with marginal fill material, and the example of minor waste being used as a sub-ballast material in a railway, retaining walls constructed with recycled construction demolition residues as backfill, and an example of the application of RCDR in geotextile encased granular columns. Then an example of geosynthetic and alternative materials in geoenvironmental application, and we finish the presentation with some final remarks. So let's start with the introduction. As probably most of you know, geosynthetics are materials that can be used with different functions in geotechnical engineering works, such as drainage, to help the water or any liquid to leave the soil. It can also be used in separation works when we want to avoid the contamination of a good quality fill material, for instance, from fines from the subgrade, from the soft fine subgrade. Can also function as a filter when we want the liquids to pass through the geotextile but want to retain the soil particles. It can also be used as a barrier in the case of geomembranes, for instance, when we want to prevent the contamination of the foundation soil by some pollutant liquid. It can also be used as a reinforcement to reinforce a soil mass to increase its strength and decrease its compressibility, and also to protect the soil, for instance, in erosion protection works. Let's see some examples of sustainability of works with geosynthetics when we use with conventional construction materials. For instance, in the case of a paved road, we can have the geosynthetics, for instance, a geotextile impregnated with asphalt can be used to avoid the piping of fines from the base soil when the base material is saturated. So with the geotextile impregnated with asphalt, we create here a barrier that avoids the passage of fines from the base layer through cracks in the asphalt cap. It can also be used as a reinforcement for the asphalt cap to the layer to avoid crack reflection. Or at the base of the pavement base layer as a reinforcement. This type of application, as the other, will increase the life of the pavement. So the benefits are greater life of the pavement, less maintenance work, less use and exploitation of natural materials, and less environmental impacts than conventional solutions in pavement engineering. For instance, we can see here two designs for a pavement: the conventional approach, where you have here an asphalt layer, gravel layer, base material consisting of a mixture of sand and gravel, and the subgrade. And here solution using geosynthetic reinforcement, the same materials in both cases, but with the presence of the reinforcement, we can reduce the thickness of the base layer. So what are the implications in terms of environmental impacts? So these researchers here, they investigated that, and here are some results that they presented, comparing the reduction or presenting the reduction of some environmental impact parameters when we use geosynthetics in comparison with the conventional pavement design solution. So here parameters, you see here parameters like acidification, eutrophication, gases that contribute to the global warming, consumption of non-renewable energy, consumption of renewable energy, and water consumption. So you see that the solution using the geosynthetic reinforcement reduce the environmental impact related to these parameters. We can have significant reduction in some cases. Another example here is the case of reinforced soil retaining wall. So you see the geosynthetic reinforcement layers here. And here the comparison of two solutions for a retaining structure. Here a conventional solution of a gravity wall, concrete gravity wall, versus a solution of a reinforced wall, where the reinforced wall are just synthetic layers. So again, this type of comparison in terms of reduction of the environmental impacts with the use of the geosynthetic solution, in this case, you can see a significant reduction in most of these parameters. For instance, approximately 81% reduction in the emission of gases that contribute to global warming, and also approximately 7 to 75 reduction in the consumption of non-renewable energy and renewable energy, and also a significant reduction in the consumption of water. Another comparison with regard to retaining structures, conventional gravity wall, cantilever wall, and here geosynthetic reinforced wall. And in these results, you see the amount of emission of CO2 as a function of the wall height, and you can see that the solution with geosynthetics reduces, or the emission of CO2 is much smaller for the solution with geosynthetic than for the conventional solutions. The same with regard to energy consumption, much less energy consumption in the solution with geosynthetics than in the conventional solutions. So geosynthetics can already provide sustainable engineering solution when we use conventional construction materials like normal, usual soils. So let's see now the combination of geosynthetic reinforcement with some marginal soils, so that will not be used in a routine basis, and also the combination of geosynthetic reinforcement with some alternative construction materials. Which type of alternative construction material can we consider? We can consider, for instance, the use of geosynthetics with PET bottles or wasted tires that can cause severe environmental impacts if they are disposed in the wrong way. For instance, these are examples of environmental impacts. So cause environmental damage and also allowing the presence of organisms or animals that may pose public health hazards. And if a pile of wasted tires caught fire, it's a very difficult fire to extinguish, and the pollution is clear here to the atmosphere. So let's see some example of this type of combination. In the case of an unpaved road, so the presence of the geosynthetic reinforcement in an unpaved road can bring several benefits. For instance, if it is a geotextile used as a separator, then the presence of the geotextile will avoid the contamination of the good quality fill material by fines from the subgrade. The geosynthetic reinforcement also carries parts of the load that would be transferred to the foundation soil, so it provides a favorable stress distribution to the foundation soil, so it increases its bearing capacity. As the reinforcement deforms with the deformation of the fill, it is stretched, so it develops tensile forces, and the vertical components of these tensile forces provide additional resistance to the continuing of the settlement of the fill material. So this is called the membrane effect. So this increases or reduces the deformability of the road. And if we use an additional layer here for drainage, geosynthetic for drainage, or we are using geocomposite for reinforcement, which also provides drainage capability, we speed consolidation of the soft soil, increasing its undrained strength. So let's see an example of an unpaved road constructed with a marginal fill material. So the road was constructed on a very soft organic clay in the Fluminense Plains in Rio de Janeiro, Brazil. it was subjected to a very heavy traffic of heavy trucks. The reinforcement used was a non-woven geotextile, which was the only type available at that time. We are talking about a case history in 1980. But at that time, we only had non-woven geotextile, which would not be the most convenient reinforcement to be used today. Today we have much more stronger and stiffer reinforcement. But this one was the one available at that time. Different types of reinforcement installation were investigated, and the fill material was a suitable fill material for this type of application because it was a very fine fill material with 66% of its particles passing the 200 C. You see here the variation of enduring strength of the soft foundation with an average enduring strength of approximately 10 kPa, very soft material. And here an image during the construction of the road. As I mentioned before, we investigated different types of installation of the reinforcement. So in experimental section S1, the reinforcement was just below the platform of the road in a way to investigate the influence of less anchorage of the reinforcement and also to provide what would be a less expensive solution in terms of reinforcement cost. Sections S2 and S3 were the reference sections which were unreinforced. In section S4, the reinforcement was placed at the base of the field. In section S5, the extremities of the reinforcement were folded to increase the anchorage and to try to increase even further the anchorage of the reinforcement. Section X6, the extremities of the reinforcement were fixed to wood beams attached to wood piles to try to increase even further the anchorage of the reinforcement extremities. So the instrumentation of the experiment consisted of full profile settlement gauge to measure the settlements at the base of the road, magnetic extensometers at the top of the clay layer to provide strains at the surface of the clay layer, magnetic extensometers in the geotextile reinforcement to assess strains in the reinforcement, and at the end of the experiment, the fill thickness was determined to check if the presence of the reinforcement decreased the required thickness of the road. So here you see some results in terms of settlement profiles in different experimental sections, where the red curve is the result for the reference section, where you can see a significant settlement here, which was actually a bearing capacity failure under the wheel of the trucks. And you see to some extent the same behavior for the section S1, but the less settlement than the reinforced section, but a similar behavior. But in the other sections, you see a more uniform distribution of settlements along the road base and less settlement. The same type of bearing capacity failure was observed in the unreinforced section S3, but in the section, the unreinforced section S3, the failure was more intense, so it damaged the instrumentation, and that unreinforced section was then abandoned. As I mentioned, at the end of the experiment, the fill thickness in each section was determined, and even using very fine materials as fill material and less anchorage, section S1 provided approximately 10% reduction in the road thickness, and this reduction increased as we increased the anchorage of the reinforcements, reaching between 16 and 23% for this type of situation. So even using a fine grain material as a fill material, which is not the most of the appropriate material to be used in this kind of application, and a reinforcement that is not also the most convenient one. Even so, we achieved satisfactory performance and a good performance of the unpaved road with a marginal soil as fill. Here's another example of an unpaved road study, in this case a large-scale equipment where to simulate an unpaved road subjected to a load at the surface. Actually, it was a cyclic load with the same intensity of the pressure expected from a truck, and a cyclic load to simulate what would be the traffic on the road, the fuel layer, and a subgrade with a CBR, California bearing ratio of 4%, and here you see the reinforcement layer. So in this test, you see the properties of the soil used in this experiment, the subgrade material in terms of particle sizes, and CBR 4.2, liquid limit, plastic limit, and two types of fuel material I used. In the first case, a conventional gravel layer. You see the properties of the gravel, and also in another experiment, the fuel material consisted of recycled construction demolition residues, and here you see the main geotechnical properties of these residues. The reinforcement used were three geogrids. Geogrid 1 was the steepest one, with a tensile stiffness of 1500 kilonewton per meter and aperture dimensions of 30 by 30 millimeter. Geogrid 2 had a tensile stiffness of 260 and aperture dimension of 20 by 20. And Geogrid 3 was the most extensible one with a tensile stiffness of 130 kilonewtons per meter and apertures of 40 by 40 millimeters. So here you see some results of unreinforced tests in terms of vertical displacement of the loading plate at the surface of the road as a function of the number of load repetitions. So the red curve is the result for the unpaved road constructed with the conventional gravel, and the blue curve the result for the road constructed with recycled construction demolition residue. And you see they both reach the maximum vertical displacement allowed at the surface of the road of 25 millimeters, approximately at the same number of load repetitions. This figure shows results for the reinforced tests. Again, the red curve is the result for the road built with gravel, and the blue curve is the result for the road construction with the RCDR fill material. So you see that in this case, the maximum vertical displacement at the surface it's reached for the RCDR fill material for a much greater number of load repetitions. If we check the value of the traffic benefit ratio, which is defined as the number of load repetitions in the reinforced case for a given settlement at the surface of the road, divided by the number of load repetitions in the unreinforced case for the same settlement at the surface, we reach a TBR value of approximately 15, showing that the presence of the reinforcement allowed the use of recycled construction demolition residues as a fill material for the unpaved road. This figure shows the vertical displacement profiles at the surface of the road. The red and black lines here are the result for the unreinforced roads built with gravel and with residues, and the blue and green curves are the results for the reinforced roads built with gravel and RCDR for a number of load repetitions of 630. So this is the number of load repetitions where the 25 millimeter vertical settlement at surface of the road was reached for the unreinforced section. So see the reduction in the surface settlements with the use of reinforcement, particularly in the case of the use of recycled construction demolition residues. So let's see now an example of the combination of poor quality fill material with geosynthetics here in a paved road. So the reference section here is the pavement built with a mixture of a fine soil and crushed rock, with 1 part of fine soil for 4 parts of crushed rock. This other section is a section of a pavement with the fine soil, a mixture of fine soil and 2% of lime to improve the fine soil properties, and 3 other pavement sections with the use of geosynthetics. Here in this case, a geotextile, no geotextile layer impregnated with asphalt below the asphalt cap. Here, the novel geotextile at the base of the pavement to function as a capillary barrier and to some extent as a reinforcement as well. And in this section, the asphalt impregnated geotextile envelope the fine soil to maintain, to keep its moisture content constant. So in these 3 sections with geotextile, only the fine soil was used as a base material. So here you see some images of the construction of the test sections, the installation of the geotextile, some field plate load tests executed, and the impregnation of the geotextile with asphalt emulsion in one of the sections tested. This table shows the properties of the fine soil used as pavement-based material in terms of liquid limit, plasticity limit, plasticity index, and a TRB classification A75 and a USCS classification as MH. And the CBR of the fine soil obtained in the laboratory test on inundated samples was equal to 17%. This table shows the main geotechnical properties of the base materials, not just the fine soil, but the mixture of soil and lime in terms of liquid and plasticity, the limits and the classifications by TRB and USCS. And here the geotechnical properties, the main geotechnical properties of the soil and crust rock mixture. Continuing the properties of the base soils, the maximum dry density, the values of maximum dry density of the materials, the optimum moisture contents for each base material, swelling index, and CBR, California Berry ratio for the fine soil, for the soil lime mixture, and for the soil crushed rock mixture, showing much higher values than that of the fine soil. Well, so let's see some results in terms of field plate load tests to determine the base reaction modulus. So here you see the results for the different test sections, showing that the sections, both at the end of construction and 4 years in service of the road, showing that the combination of fine soil and geotextile provided similar or even greater results than the results obtained for the standard soil crushed rock mixture as a base material or the fine soil mixed with lime. The results of pencil pressure meter tests on the base soil, again the results obtained at the end of construction of the road and after 4 years in service, showing also very good performance of the combination of fine soil and geotextile in the base layer. In terms of Benkelman beam test results on the base layer, in terms of soil models to to the different test sections, and again the results for the combination of fine soil and geotextile comparable to, or in some cases even greater than those obtained in the standard solutions for base soil stabilization. Again, the results of Bankman being tested now in terms of deflection along the distance. There you can see here the results for the soil crust rock section is the red curve, and you see the good result obtained, particularly for the section where the geotextile, the asphalt impregnated geotextile enveloped the base layer, which is the blue curve here. Here, after 4 years in service, here at the end of construction, here, after 4 years in service, and in this case, the results are very similar, showing again the good performance of the combination of fine-grained soil and geotextile in comparison with the standard solutions, the common solution used. Again, here, results of follow-away diffractometer test, FWT test at the end of construction, and after 4 years in service, results of soil crust rock base material, and the results for the soil line and the combination of geotextile. And the fine-grained soil show also good performance of solutions using the combination of fine soil and geotextile. So this combination provided satisfactory behavior of the pavement using poor fill materials because it was a fine-grained fill material. So here an example of the combination of geosynthetic reinforcement with an alternative subballast material in a railway. The railway in question is the Victoria Minas Railway, which is a very busy railway which belongs to the Vale Mining Company and is subjected to a very heavy traffic of trains carrying mining goods. Very busy railway in Brazil. It has something like it's something like 800 kilometers long. So here you see a cross section of the test sections, and the objective of the research was to investigate the possible use of an alternative subballast material for the railway. This slide shows the description of the materials. The alternative subballast material consisted of a mixture of 50% of a local soil, a silty sand, plus 25% of a fine mining waste, a sandy silt, plus 25% of the conventional subballast material that has been commonly used. The subgrade soil consisted of a silty clay sand with 16% of clay, with a CBR of 6-7%, and a Young modulus of the surface compaction of 100 megapascal. The reinforcement used was a GeoGrid with 30 by 30 millimeter apertures, manufactured with polyester fibers with a PVC cover, a tensile strength obtained in wide strip tensile test of 65 kilonewtons per meter, maximum tensile strain of 10%, and a tensile stiffness at 5% strain of 520 kilonewtons per meter. So here you see an image of one of the test sections with the type of trains that passed on the test section. Another image here, in a view of the railway track. Here the installation of strain gauge in the subballast layer, and here Bankman beam test being carried out in one of the test sections. It is important to point out that the same traffic that passed on the railway was the one that passed on the experimental section. So the test section was subjected to the same traffic of trains that took place in the real railway. This graph shows the grain size distribution curves of the materials. The blue curve here is the grain size distribution for the ballast, material. The black curve is the subgrade, as the particle distribution for the conventional subballast material that has been commonly used. And the red curve is the grain size distribution curve for the alternative subballast material, where you can see that this alternative material is much finer than the conventional subballast material. This image, this drawing shows the typical cross-section of the test section. Section S1 was the reference section, which was built with the conventional subballast material. In sections S2 and S3, we had the geogrid reinforcement. In section S2, at the base of the alternative subballast material. In section S3, at the top of the alternative subballast material. And section X6 was also constructed with the alternative subballast material, but without geogrid reinforcement, just as a comparison to see how the alternative subballast material would behave under unreinforced conditions. So here we have some results in terms of Bankman beam test results, where the red curve here is the result of deflection along the distance for the reference section with the conventional subballast material. And you see that the results obtained with the reinforced alternative material were very similar to that of the conventional subballast material, showing that the presence of the reinforcement increased or improved the performance of the alternative subballast material. This can also be seen with the result for the test S6, where the alternative subballast material was used without reinforcement. In this case, the deflection was much higher than in the case with the reinforcement, the geogrid reinforcement. Here you see some results in terms of vertical strains in the subballast as a function of the number of load axles that pass on the railway. So the red curve is the result for the reference section. Large settlements at this stage for the section with just the alternative subballast material, and smaller strains in section S3 with the presence of the geogrid reinforcing the alternative subballast material. And this graph shows results in terms of horizontal strains in the subballast layer as a function of number of axles that pass on the railway, train axles that pass on the railway. And again, the largest strains were observed for the unreinforced alternative subballast material. And here the results for the conventional subballast material, and again, less strains observed in the section reinforced with geogrid. An additional benefit of the presence of the reinforced was the reduction in ballast particle breakage. So you see results of percentage of particles of the ballast layer that were broken as a function of time, monitoring of experiment or number of axles of trains. So the red curve here is the result for the conventional solution with the conventional subballast material, and followed by the result for the section with just the alternative and unreinforced ballast material, and less breakage of ballast particles or ballast grains in the sections with the alternative subballast material reinforced with geogrid. So an additional benefit of the presence of the reinforcement is the reduction of breakage of ballast particles, which has an interesting repercussion in terms of reduction of costs of maintenance of the railway track. So the geosynthetic reinforcement allows the use of an alternative and cheaper subballast material for this railway. Let's see now an example of the combination of recycle construction demolition residue as backfill in geosynthetic reinforced walls. So here you see a cross-section of the experimental walls, a 3.6 meter geosynthetic reinforced wall, constructed on a porous collapsible soil, which is a very common soil in the city of Brasilia, where this experiment was carried out. And the novelty of this research was the use of recycled construction and demolition residue as a backfill material for the reinforced structure. So the sections were instrumented with strain gauge to measure reinforcement strains and total stress cells, and also inclinometers at the toe of the wall to access horizontal displacement of the foundation soil. So here you see an image of the experimental walls. Wall 1 was reinforced with geogrid, and wall 2 was reinforced with a non-moving geotextile. Because the walls were constructed on a collapsible soil, a part of the investigation also studied the influence of the foundation soil collapse caused by inundation. This type of soil, its fabric structure can collapse when you increase the moisture content. So this pools here allow the inundation of the foundation soil, because at the base of the walls there was a drainage layer, so the water could infiltrate in the foundation soil, causing its collapse. So the objective here was to check the performance of the wall under the conditions of the foundation soil collapse. So here you see an image of wall 1 reinforced with geogrid at the end of construction, and here you see an image of the face of wall 2 reinforced with non-wood geotextile. Because in this region you don't have confinement of the geotextile, you see a more significant bulging of the reinforcement than in the solution with geogrid reinforcement. This table shows the properties of the materials, the recycled construction demolition residue, its main geotechnical properties in terms of particle size and particle sizes, and friction angle and cohesion. And here the properties of the geosynthetic reinforcement. The geogrid of all1 was a polyester geogrid with 20 by 20 millimeters aperture, tensile strength of 20 kilonewtons per meter, second stiffness at 5% strain of 300 kilonewtons per meter, and a strain at break of 12%. The non-woven geotextile used in wall 2 was a polypropylene geotextile with a tensile strength of 24 kilonewtons per meter and a second tensile stiffness of 15 kilonewtons per meter under unconfined conditions in air tensile tests. But if the geotextile is tested confined in the soil, then its tensile stiffness can increase significantly, varying between 160 to 180 kilonewtons per meter, so comparable to some extent to the tensile stiffness of the geogrid used in wall 1. The instrumentation of the walls consisted of strain gauge to measure strains in the reinforcement, in the geogrid reinforcement, and telltales to measure strains in the geotextile reinforcement, total stress cells to measure horizontal and vertical total stresses, and wall face displacements were also measured. And here you see some image, the gluing of strain gauge in the geogrid, and total stress installation in the field, and so on. Let's see some results here in terms of settlements along the wall top. Here we see the settlements normalized by the height of the wall along the top of the wall. So here you see the profile settlement for wall 2, reinforced with geotextile, very uniform settlement profile 1 year after construction. And here you see the profile obtained for wall 1 rainfall geogrid, greater settlements, but these greater settlements were caused by the greater collapsibility and greater compressibility of the soil of the foundation beneath the section wall 1. So the foundation soil under wall 1 was more compressible than under wall 2. And after here you see the settlement after the foundation soil collapse caused by the inundation of the foundation soil. So you see an increase, a significant increase in settlements caused by the collapse of the foundation soil, but still a very uniform profile of settlements for wall 2 and a not so uniform or greater settlements for wall 2 because of the greater compressibility or collapsibility of the foundation soil under wall 1. Here results in terms of strains in the reinforcements for wall 1 and wall 2. Before and after inundation, you don't see much difference between the results, not a significant influence of the inundation of the foundation soil on the strains. And same for wall 2, but you can see here larger strains close to the face of wall 2 because of less confinement of the geotextile in this region. So much greater strains than in the case of the geogrid reinforcement in wall 1. This graph shows results of wall face displacements before and after subgrade inundation. So you see here the red curve is the result after foundation soil inundation, the black curve the result before. So you see some increase of wall face display, horizontal displacement due to inundation, both in wall 1 and in wall 2. But in wall 2, because of the bulging of the reinforcement, due to less confinement of the geotextile, you will get greater horizontal displacement. But if we get the horizontal displacement a bit inside the reinforced mass, where you have an increase in the tensile stiffness of the geotextile, you see less horizontal displacements in that region and values comparable to those obtained in the geogrid reinforced wall. You see results of maximum tensile strength in the reinforcement as a function of the cumulative precipitation, the precipitation water from the rain during the rainy period. For 3 reinforcements here, reinforcement layer 1, layer 3, and layer 5. And you can see some increase in the maximum tensile strength due to the infiltration of water from the rain, because it increases the unit weight of the pure material and also causes some level collapse of the foundation soil. Here results of horizontal displacement of the foundation soil 1 year after construction and after inundation of the foundation soil. So you see similar results for wall 1 and wall 2 1 year after construction and after inundation of the foundation soil. You can see that we get an increase in the maximum horizontal displacement, but again, for the similar results for wall 1 and wall 2. So this study validated the use of recycled construction demolition residue as a cheap backfill material for geosynthetic reinforced walls. Another application that we can have for recycled construction demolition residue is as infill material for granular columns, particularly geotextile case granular columns. So granular columns can be used to stabilize an embankment constructed on a soft foundation soil. So the idea here is to have most of the load from the embankment to be transferred to the rigid granular columns, and the granular columns transferring this load to a stiffer and stronger soil layer below the soft soil layer. So this is the idea behind the use of granular columns. But the conventional granular columns, they have a shortcoming, which is that when it is loaded by the embankment, because of the low confinement provided by the soft soil, the top of the column tends to bulge. So this will reduce the efficiency of the conventional granular column in reducing the settlements of the embankment. So if the column is encased by a stiff geotextile, woven geotextile, this will reduce or avoid bulging at the top of the column, so the efficiency of the granular columns will increase in terms of embankment settlement reductions. So here you see an image of a granular in geotextile encased column. Usually the infill material used is sand or gravel. So a large-scale experiment was conducted to investigate the use of recycled construction and demolition residue as infill material for the geotextile encased column. So we have here the column encased by a geotextile. Instrumentation of the subsoil consisted of pressure cells and also pore pressure transducers. And despite the size of the equipment, this is actually a model test. So the diameter of the column was 150 millimeters, which would give a scale factor, geometric scale factor between 4 to 6, depending on the diameter of the prototype column considered. So here you see the properties of the geotextile used as encasement. Of course, because of the model conditions, it had to be modeled accordingly. So we have here 3 types of geotextiles that were used as encasement with tensile strength between 8 and 30 kilonewtons per meter, maximum tensile strength between 15 and 22%, and tensile stiffness at 5%, tensile strain between 53.4 kilonewtons per meter and 120 kilonewtons per meter. This table shows the main geotechnical parameters of the soils used as infill materials for the columns, the sand material in terms of particle sizes, void ratio, and friction angle, elevation angle, the gravel. One of the columns, some columns were built with conventional sand, conventional gravel. Here are the properties of the gravel used. And here the properties of the recycled construction demolition residues used as infill material for the granular column. So you see that they have similar values of friction angle and dilation angle. This table shows the properties of the soft soil in terms of liquid limit, plasticity index, and parameters obtained, compression index and swelling index obtained in consolidation tests. And this graph shows the grain size distribution curve of the fine-grained foundation soil, the sand used in the granular column, and the grain size distribution curves for the gravel and the RCDR materials, very similar curves. This was on purpose to compare the gravel with the RCDR with similar values, similar dimensions of particles. So let's see some results obtained in the load tests carried out. So here you see results of settlements at the top of the granular column as a function of the load applied. So the black curve is the result for the sand column in case of geotextile, the blue curve for the gravel column, and the red curve for the recycled construction demolition residue column. So you see very similar load capacity for the 3 infill materials used. This graph shows results of load capacity for the different types of columns tested. You should be pointed out that this scale is a log scale because here you have results for the conventional columns without the presence of the geotextile. So the load capacity of the conventional column is much lower than those of the geotextile encased columns. So, but you can see in this graph that the performance of the cycle construction demolition residue as an infill material was very good. So comparable results with the use of the conventional infill material. So the cycle construction demolition residue can also be used as infill material for granular increased granular column for stabilization of embankments on soft soils, for instance. Let's see now the combination of geosynthetics and some alternative materials and some environmental applications. Here you see the alternative construction materials that we can think of. Recycled construction demolition residues, again, wasted tires, the whole tire or tire chips, or for instance, compressed PET bottles to function in a similar way as stones or gravel. So let's see an example of comparison between alternative drainage system and conventional drainage system in experimental municipal solid waste cells. So here you see a cross-section of experimental municipal solid waste cell with 50 tons of waste, but using a conventional drainage layer consisting of a gravel layer. So you see here a geomembrane and the gravel layer, 50 tons of municipal solid waste. So the cells were instrumented with temperature gauge and also resettlement plates inside the waste mass. The alternative drainage system consisted of a drainage layer consisting of tires and a geotextile filter. Okay, same municipal solid waste, same amount of waste, 50 tons, on the same subgrade and also with a geomembrane layer at the base. And this drainage trench here consists of tire chips and the geomembrane here. So in this image you see the construction of the alternative experimental drainage layer for this waste cell. Properties of the material, the municipal solid waste, the main composition of the waste with approximately 50% of organic matter. The soils, the gravel soil used in the conventional drainage layer in terms of particle size, coefficient of uniformity, unit weight, and coefficient of permeability. The properties of the cover soil, of the experimental cells, and the properties of the geotextile filter, a non-woven geotextile with 150 grams per square meter, mass per unit area, 1.5 thickness, millimeters thickness, permeability coefficient of 0.4, permittivity equal to 2.5, and a filtration opening size of 0.15 millimeters. So let's see some results here in terms of leachate effluent volume as a function of the time of monitoring. The red curve is the result for the conventional gravel drainage layer, and the blue curve is the result obtained for the alternative drainage layer consisting of tires. So you see practically the same result. This region here is where you see less effluent volume is occur during the dry season in the region. So here see results in terms of suspended solids in the leachate, in the effluent, as a function of time. You can see the result here for the conventional drainage layer consisting of gravel, and this result here for the alternative drainage layer consisting of tires and the geotextiles. So less suspended solids in the alternative drainage layer because of the presence of the geotextile filter. Other alternatives or other use of or other combinations of geosynthetics and alternative drainage material, here in this case in the drainage layer in the landfill. And here the drainage layer consists of whole tires with a geotextile filter. In this case here, a drainage trench where the drainage material was consisted of tire chips and also combined with a geotextile filter. In this case here, you have a drainage trench for a road, and the drainage layer here consisted of compressed PET bottles combined with a geotextile filter. So these are combinations that can be used to give a better use to wasted materials such as tires and PET bottles, and also maybe very interesting in regions where natural materials are scarce or very expensive, or their use is limited because of environmental protection regulation or laws. Okay, so we reached the end of this presentation, so some final remarks on this slide. The geosynthetics can provide sustainable engineering solutions when they are used with conventional soil. We saw that they can provide engineering solutions that cause less impact to the environment than conventional engineering solutions. Waste and marginal soils may be used associated with geosynthetic reinforcement, but also to provide cheaper engineering solution. Feasibility of using marginal and waste material increases the sustainability potential of geosynthetic applications. So if they already provide sustainable solution when we use conventional construction material, if you use marginal or waste materials, we will increase even further the sustainability of the solution. And combination of geosynthetics and recycled construction demolition residues and mine waste are particularly interesting because a huge amount of recycled construction demolition residues and of mine waste are generated on a daily basis. So the use of such construction materials will certainly provide a better use of this material instead of disposing them in landfills or in the nature, causing important environmental impacts. So I would like to finish this presentation thanking again for the invitation made by the organized committee, and thank you very much for your attention.
Thank you very much, sir. Thank you very much for giving insight of the issue. Like, I think you have covered all the aspects of application of geosynthetics in the field of geotechnical and geoenvironmental engineering, and also you have addressed issues of using alternate construction materials like utilization of waste. And I really appreciate your invention on RCDR, recycled construction demolition residues. And I'm sure that from your presentation, future researchers, scholars, and students must have been benefited. Let me take some questions that has been asked in the chat box. If someone has a question, they can unmute also and they can ask. But let me first read whatever has come in the chat box. So there is a question from Bhatia. He's asking for retaining walls, what is the cost variation between conventional gravity and geosynthetic supported retaining wall? He's asking about the cost variation.
Well, it certainly depends on the local cost of the material, but it's very common in most of the situations. The net reinforced wall is cheaper than the conventional walls, and not only cheaper, but it's getting more and more popular because of the less environmental impact it causes in comparison with the conventional solution as well. So besides being cheaper in, I guess, most of the cases, not all cases, it also has the attractive aspect of providing a more environmentally friendly solution, which is becoming more and more important because of the concerns regarding environmental protection.
That is true. That is true. There is another question from Anil Singhai. Okay. Several methods of blending material is available. So out of them, although he has not mentioned those materials, but then he is expecting that you have good experience in the field and you have good experience in the blending materials. So he is asking which one is the most effective and economical material you think from your expertise, from your experience.
I can see recycled construction demolition residue has a great potential because it's a huge amount is generated. For instance, in the city that I live in Brasilia, almost 70% of the material that is disposed in the landfill is construction demolition residues. So at the end, you occupy the volume of most of the volume of the landfill with a material that could be better used in geotechnical engineering works. So I see the use of construction and demolition residues with great potential in geotechnical engineering. And if combined with the geosynthetic reinforcement, it will certainly provide a cheaper solution for embankments or, for instance, reinforced wall. PET bottles, as I presented, they can also be used. We have used here in Brasilia as drainage material compressed PET bottles because the gravel, particularly in the city where we live, Brasilia, is very expensive because it comes from distant sources. We have gravel closer, but they are in areas that are protected, environmentally protected, so we cannot exploit them. So we have to bring gravel from distant places. So at the end, the use of any alternative drainage material provides a cheaper solution than the use of gravel. But the problem with some of the wastes or some of the residue is that they have also demand for other applications. For instance, PET can be recycled for other applications. So we have a competition. The construction industry has a competition for other industry that recycle this type of material, recycle tires, recycle PET bottles. So, but where in regions where you have abundant PET bottles and tires, and in landfills particularly, you can find a better use for these materials, and they can certainly be combined with geotextile or fuels or geogrid as reinforcement to give a better and more environmentally friendly solution.
Yeah, I think confinement option is giving better opportunity for our CDR. Uh, Otherwise, I've seen the treatment, chemical treatment of recycled aggregate. That becomes little costly because you have to meet the requirement of aggregate as a construction material for the construction of payments and other things. But definitely, as you mentioned, that if material natural aggregate is environmentally protected, then we have to be dependent on alternate materials. And this utilization of waste is actually the best option nowadays. So a lot of research is going on. That's a good
Yes,
thing. And
mine waste, because if you can use mine waste in construction, you will avoid, for instance, tailing dams or reduce the volume of in tailing dams and accidents in tailing dams. But we have had recent very serious accidents with tailing dams in Brazil. So if you find a better use for mining waste, is also very
yes.
interesting to the environment.
Yeah, and there is a question from Adek. He is asking, uh, if there is a potential effect by liquefaction, is it still possible for using geo-grade materials? How to make sure that material is still safe?
Well, fortunately, we don't have earthquakes in Brazil, so I'm
Okay.
not that experienced in seismic behavior of structure. We have some regions in Brazil, in the Amazon or in the southern states, where we are closer to countries that have earthquakes, like Argentina and Colombia. And when there's a strong earthquake there, we have some vibrations in some cities in Brazil, but nothing compared to earthquakes that you will find occurring in countries like Japan, Chile, and other places in the world. But anyway, if you have a reinforcement in the soil mass, etc., will help avoiding failure if you have a seismic event, or if you have liquefaction, the presence of the reinforcement or the presence of the geosynthetic as a drainage layer that would help dissipating the pore pressure generated during the seismic event, it will certainly help. So there is experience in other countries where they have earthquakes that people use in geosynthetics as reinforcement or as drainage material to avoid or minimize failures and deformations caused by seismic events in countries. Like Japan, for instance, they have a large experience in using geosynthetic reinforcement in earth structures in seismic regions and in regions with very, very strong earthquakes.
Okay, so I think many of you, many of my participants, they want to interact with you, and I have received a lot of appreciations for your presentation. Also, it was
Thank
very
you.
informative session, and so and so forth. Uh, I know that it is midnight over there, so I will not extend my interaction because I know there are many questions here, but then they can ask you, they can search you over internet and they can find. Otherwise, I'll share your email ID and they can interact with you whenever they want. So
Sure.
I thank you very much, sir, once again for taking pain and being with us. Uh, and now I request my co-chair to give vote of thank and close the session.
Thank you very much. Thank you.
Thank you very much, sir, for taking up the queries of our audience. On behalf of School of Civil Engineering, Lovely Professional University, IGS Jalandhar Chapter, and Department of Civil Engineering, NIT Jalandhar, and from the entire team of faculty members and students, I'm thankful to you for spending time with us.
Thank
We
you very
wish
much.
you all the good health and prosperous life ahead. As a token of appreciation, please accept our e-certificate of appreciation.
Thank you. Thank you very much.
I hope you can
Thank
see,
you,
sir.
sir.
Hope you can see this certificate.
No.
Okay, let me
Yes.
confirm. Huh?
Yes, now I can see. Thank you very much.
Yeah, I just wanted to confirm that you can see. So, good night to you, sir. Take rest. Thank you.
Bye-bye. Stay safe.
Bye bye. Thank you.